Yes, students, in the class, we are going to discuss few models for blood flow. First, we will see that what is the Navier-Stokes equation. For the blood flow. So here we are considering few concepts. That is Navier-Stokes equation, and then it is that viscous incompressible flow. These are the assumptions. One is viscous, one more is that is incompressible flow. For the fluid, we are going to find that what is a Navier-Stokes equation. First, we are taking that few velocity. What are the velocities of u, v, w are the velocity, and these are the functions of x, y, z, and p is that pressure of the fluid, which is also the function of x, y, z and t. And then it is an incompressible fluid, therefore the viscosity is that constant. Rho is the viscosity, and it is the constant. And we'll consider mu. Mu is that viscosity coefficient. Oh, this rho is not that viscosity, constant density. Rho is the constant density. Constant density of the fluid. Then what is the equation of continuity? Equation of continuity is expressed in the amount of fluid entering unit volume which unit time, the same as that amount field leaving that per unit time. So that means if you consider any fluid element here, that is the number of fluid entering into that, and then the same amount will be existing from the unit. So that is consider in that unit time. This unit time t, how many entering particles and existing molecular particles. Okay, so then it is at mass conservation. Therefore, we can write this equation is dou E by dou x, dou U by dou y, dou V by dou y, not dou U, dou V by dou y, dou V by dou y, dou W by dou Z equal to 0. You take this as equation number 1, and then you can see here it is that independent of time t. Independent of time t. So how can we obtain the equation of motion based on the Newton's second law of motion? Equation of motion for the blood flow that is based on the Newton's second law of motion. What is Newton's second law of motion? Can you guess it? That is force equal to mass into acceleration. That means F equal to mv. It is the Newton's second law of motion. That is what is it states? Newton's second law of motion, which states that the product of mass and acceleration of any fluid element is equal to the resultant of all the external body forces. So acting on the element, and so the surface forces acting on the fluid volume due to the action is remaining fluid on the same element. The equation of motion known as the Navier-Stokes equation, then the Navier-Stokes equation can be written as for that rho dou E by dou T plus U dou E by dou X plus V dou E by dou Y plus W dou E by dou Z equal to X minus dou P by dou X plus mu into dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square, which is equation number 2. So this one can be written as simply we can write as rho d v by dt or dq by dt. V is the velocity here, that is equal to, the next is the direction, xi minus dou p by dou xi plus u into del square u. Simply we can write as, in case if you are writing that q here, q as the velocity, here also we can write that as q. Okay. Then if you are expanding this Navier-Stokes equation for that another direction v and w, then we will get that rho, I can change the pen color, yeah, rho dou v by dou t plus u dou v by dou t plus v dou v by dou t plus w dou v by dou t equal to y minus dou rho by dou y plus mu into dou square u v by dou x square plus dou square v by dou y square plus dou square v by dou z square. This is equation number 3. Then rho dou w by dou t plus u dou w by dou t plus v dou w by dou t plus w dou w by dou t. that is equal to z minus dou rho by dou z plus mu dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square, which is equation number 4. Then what are the x, y, z here? X, y, z is the function. In case the function f can be written as xi plus yj plus zk, then x, y, z are known as the components of external forces for the conservative system. So in case if it is any pi is that potential function is there, pi is that potential function, then in case f is a conservative system, f can be expressed as del pi. You know this, what is del? Del, you know that I dou by dou x plus j dou by dou y plus k dou by dou z. So f can be expressed as dou pi by dou x I plus j dou pi by dou y plus k dou pi by dou z. Therefore x equal to dou pi by dou x, y equal to dou pi by dou y, z equal to dou pi by dou z. Therefore we can write that x minus dou p by dou x equal to minus dou by dou x of pi plus p. Similarly y minus dou p by dou y equal to minus dou by dou y of pi plus p, and similarly we can write z equal to z minus dou p by dou y equal to minus dou by dou y of not y, z, dou by dou z of pi plus p. This is equation number 5. We can write this as the whole thing as equation number 5. Then p is efficient replaced by effectively replaced by p plus pi. So x, y, z are known as, are option 1 from 1 to 4 equation. The system is the coupled non-linear partial differential equation for the 4 unknowns u, v, w and p. So that equation have to be solved subject to that some initial conditions, given that motion of fluid at the time t equal to 0 and certain prescribed boundary conditions. So in case if x, y and capital Z are unknowns, are absent from 1, 2, 3 and 4, . not option from, because if it is option then we will give that 1 to 4 are the coupled system. 1 to 4 are the coupled equation. As the coupled equation, we are going to find that the four unknowns u, v, w and p is there. What are the unknowns here? Unknowns are u, v, w and p. We have to solve for this u, v, w and p. So this equation can be solved by using that some initial conditions. Giving the motion of the fluid at time t equal to 0 under certain prescribed boundary condition on the surfaces, which will be fluid, maybe contact or conditions which may hold a very large distance from the surfaces. So generally, either we have to use that some initial conditions or some boundary conditions. Based on that initial conditions or boundary conditions, we are solving at the time boundary conditions at the time t equal to 0. So generally the boundary conditions are there. No? The boundary conditions are given as a no slip boundary condition. The boundary conditions are the no slip boundary conditions. So which are the both tangential and normal components. Both tangential and normal conditions. Components. Okay. Now the fluid velocity will be vanish at all points of the surfaces of the stationary body with will be fluid may be that contact. However, if the body is moving, then the tangential and the normal components of the fluid velocity at any point of contact are the same as the moving body at the point. So we may consider simply some basic equations that we will discuss very elaborately in the next class, how to find this unknowns u, v, w and p from this, and then using some boundary conditions we can solve it very easily. Then we can find that u, v and w and p from this.